In this video, we're going to look at ethers, and the functional group for the ether is the ether linkage. So we're going to write that right here. It's the ether linkage. And you can see right here, it's like an alkyl group bonded to an oxygen, bonded to another alkyl group. And that's the functional group that joins two alkyl chains. You can have ether branches like a methoxy branch and an ethoxy branch. And if you have an ether branch that involves benzene, well, we call that phenoxy. And phenoxy is because the benzene is not the parent, and you'll recall that when benzene is not the parent, we use phenol as a branch, right? You can see in the alcohol, again, benzene wasn't the parent here, so we said phenol, OL, to indicate that it's an alcohol, right? And so if we have for ethers, benzene's not the parent, it's part of the branch, so we say phenoxy, much in the same way we see ethoxy or methoxy. Okay, the larger R group is the parent, the smaller R group is the branch, and requires a number for the carbon it is attached to. So I look over here, this is my larger portion right here. It's a larger 1,2 carbon portion. This right here is smaller. It's only a 1 carbon portion. Okay, so the smaller R group is the branch, while the 1 carbon is smaller, so it's a 1 carbon branch. So I'm going to say methoxy. And then 1, 2 carbons in this one right here, so I say methoxy ethane. I look at this one right here and I see this is my longest chain, and I've got a methoxy branch, right? 1 carbon over here attached to the second carbon. So I say 2 methoxy butane. Over here, it's a bit more complicated. I have to check because my ether linkage happens on the second carbon, but I also have a halide over here as well. So which way will I number it? Left to right or right to left? Well, it depends. Does the ether have the priority or does the halide have the priority? Let's go to our priority chart. We can clearly see that ether has priority over halides, so we need to give the ether linkage the lower possible number. So I'm going to number it from the left to right, 1, 2, 3, 4, 5, 6. And so numbering it from the right, that means that this carbon right here is the second carbon, and this one over here is the 5th carbon. So then I say 5 bromo, 2, and my branch here is not 1 carbon, but 1, 2. So I'm going to say ethoxy. And my larger hydrocarbon is 6 carbons, so ethoxyhexane. When we are looking at the priority chart, our ether linkage has higher priority than alkenes. So that means I'm going to go 1, 2, 3, 4, 5, 6, 7. So this is actually going to be 2 phenoxy. And then I'm going to have to put a -4 because I have a double bond. So 2 phenoxy, 4 heptene. Okay, with the double bond taking place on the 4th carbon. Okay, so the bent geometry of the ether linkage, the COC, creates a small area of polarity with a nonpolar molecule. Bent geometry hinders molecules from getting close to each other and thereby weakening the intermolecular bonds. Boiling points are therefore typically lower or low, and ethers tend to evaporate easily, so we call that they're volatile. So comparing boiling points of similarly sized alcohols, well, these are actually isomers of each other. That's because ethanol, if we look at the formula, that's C2H5O. And if we look at this formula right here, apologies, it's not C2H5O, that's C2H6O. This one right here is also C2H6O. So these are actually what we call structural or constitutional isomers. So we'll say constitutional or structural isomers, But because of the bonding structure, you can see that ethanol has the ability to form hydrogen bonds where methoxymethane does not, and therefore has the much lower boiling point. Let's look at the preparation reactions of ethers. There's only one preparation reaction of ether, and that's the condensation of alcohols. So we take two alcohols and we put them together in the presence of an acid. So methanol and ethanol in the presence of H2SO4. Methanol would be CH3OH. Ethanol would be, this is CH2 and that's CH3, reacting in the presence of sulfuric acid. Okay, so what's going to happen here, and I'll just kind of show you, is that the H of one will bond with the OH of another. And again, you may have guessed that this is going to make water. Okay. But what is going to form here is the methyl group bonded to the oxygen right there. This now needs another bond, and this right here needs a bond, so then they link up with that ether linkage. Okay, so then we write the names of this. So the first one is methanol. This is ethanol. Okay, and this right here would be methoxyethane. And this is water right here. Ethers can also combust as well. So if we have, as we saw, C2H6O, that's methoxymethane, it can burn in oxygen and make carbon dioxide and H2O. Okay, so that's not a preparation reaction, that's a combustion reaction that has ether as a reactant. So that's basically the only reaction ether can undergo. This makes an ether, but this is the only reaction that ether undergoes. So ethers, therefore, they make good solvents for organic reactions because other than combustions, ethers tend to be chemically inert or unreactive. Therefore, ethers don't interfere with the intended reaction. They're not going to react with anything that's happening. So we can dissolve things in ethers pretty well. Since they are only slightly polar, they have the capacity to dissolve most polar and non-polar organic compounds. And because ethers are volatile, at the end of the reaction, it's easy to evaporate them off as the solvent. And this property is desirable when the reaction is finished. The product must be purified and isolated. Okay, so pretty short one there for ethers. Only two reactions. One is a preparation reaction. One is a combustion reaction where we're burning the ether. Okay, and just take a look at the properties as well and how to name them. Okay, thanks for watching.